Hi everyone. Today I'll briefly talk about how we can use Markov Chain Monte Carlo to decorrelate resampling algorithms. We'll discuss this specifically in the context of real-time rendering with the ReSTIR algorithm, though the ideas apply more generally. This is joint work with the real-time graphics group at NVIDIA. So in recent years, ReSTIR-based algorithms have greatly accelerated direct and global illumination of complex animated scenes. For instance, in this carousel scene with 3 million emissive triangles, without any denoising, the latest ReSTIR algorithms provide upwards of 100x improvement in sampling quality compared to brute force path tracing. This is because a standard path tracer traces rays independently from each pixel, while ReSTIR achieves its efficiency gains by reusing light paths with large contributions, spatially between pixels, and temporally across multiple frames. However, sharing samples over-enthusiastically can come at the cost of introducing correlation artifacts, which even state-of-the-art denoisers cannot resolve. Now, correlation artifacts are not unique to ReSTIR. Other sample reuse algorithms, such as Metropolis light transport, photon mapping, and virtual point light methods, also suffer from similar artifacts. With ReSTIR, we find this to specifically be the case in scenes with glossy materials and difficult to sample lighting. So in this work, we greatly resolve these artifacts with a simple modification to ReSTIR, where we randomly mutate a subset of the light path. We find that even with just a single mutation, we produce cleaner images in both static scenes with complex geometry, as well as in animated sequences. Moreover, by improving sampling quality, we find that denoisers automatically work much better with ReSTIR generated images. So let's now review some sampling concepts related to ReSTIR to understand why correlations arise in the first place. In real-time rendering, our goal is to estimate the light transport equation not just at every pixel in a single image, but for a sequence of images in a scene that might change dynamically over time. Abstractly, we can frame this problem as needing to estimate a series of integrals, each with a slightly different integrand and domain of integration. In standard path tracing, we estimate each integral independently at every pixel using Monte Carlo integration. But this can be wasteful, since in general, nearby integrals have pretty similar values, both spatially as well as temporally. So rather than using independent samples for each pixel, ReSTIR instead amortizes the cost of sample generation through spatiotemporal reuse. The core operation it relies on is resampled importance sampling, which, given a set of weighted samples, selects a subset of these samples in proportion to their weight W. In the context of light transport, we can use RIS to identify samples that are distributed roughly in proportion to an unnormalized target function p hat, which we set equal to the integrand of the rendering equation. So here we set the resampling weight W for each candidate sample Y to equal p hat over the sampling distribution Q, for which we typically use area or BSDF sampling. We also assign a new contribution weight, capital W, to each selected sample X, which approximates the reciprocal of the target RIS distribution. The expected value of this contribution weight times the integrand f then equals the integral we want to estimate for any given pixel. Now, this is all well and good, but with ReSTIR, we also want to resample across pixels to massively increase sampling efficiency. So here we can again use RIS, but if we apply it repeatedly to the same sample population, then we can quickly get duplicate samples, as shown here in this 1D example where the target function changes over time. Now, this sample starvation can be partially resolved by generating new independent samples every frame, but in ReSTIR, it doesn't entirely fix the issue, because the resampling weights must be modified with an MIS weight and a Jacobian determinant to account for the change of integration domain. For scenes with specular surfaces, simply reusing light paths by reconnecting vertices can lead to singular Jacobians. On the other hand, the MIS weight M assigns a confidence factor C to the p hat of the previous frame, which heuristically trades noise for correlation. In particular, setting C to a small value can cause important samples to be discarded quickly. This results in increased noise. Using a large C can end up overemphasizing the importance of samples that have survived over multiple frames, which increases correlation by causing samples to be repeatedly exchanged between several pixels. So altogether, in scenes with glossy materials and difficult to sample lighting, imperfect importance sampling and suboptimal parameters can lead to distracting artifacts, especially at low sample counts. So to mitigate these artifacts, we turn to Markov Chain Monte Carlo with the Metropolis Hastings algorithm. Similar to RIS, MCMC redistributes samples in proportion to a target function p hat, but it uses randomized mutations in place of resampling. MCMC has been studied in great depth in rendering in the context of Metropolis light transport. But by itself, it can suffer from slow convergence, especially for real-time rendering. So the key insight of our method is that we can actually overcome the shortcomings of both RIS and MCMC by simply interleaving resampling and mutations, which in turn will help to mitigate correlation artifacts. So specifically, given a set of weighted samples, resampling is very good at identifying samples with large contributions, but it leads to sample duplication. MCMC is typically slow at finding important samples, but it's a convenient way to diversify sample populations already selected by RIS. In this 1D example, we use MCMC to randomly perturb samples selected by resampling every frame, using the same target function as RIS for our mutations. Moreover, we avoid any burn-in period with MCMC by appropriately modifying the contribution weight W of the mutated sample C. The expected value of this modified contribution weight times the integrand F then gives us the correct result. This formula also works irrespective of the number of mutations we apply at any pixel, so it could be 0, 1, or even 100. In the broader ReSTIR algorithm, we reduce sample duplications by applying mutations between consecutive rounds of resampling using the same target function as temporal RIS for each pixel. Note that unlike Metropolis light transport, we do not mutate samples across pixels since our goal is diversification of RIS samples. So as with standard ReSTIR, we let RIS resample across pixels to identify samples with large contributions. In practice, we first deterministically shift map a light path between pixels during resampling, and then mutate a subset of the light path, though we can use any previously developed mutation strategy as well. Okay, so now for some additional results. First and foremost, our extension to ReSTIR applies to both scenes with direct lighting, as well as global illumination. In both cases, correlation artifacts often do not disappear by simply using more samples, which justifies the overhead of performing mutations. In general, mutations reduce short-range correlation artifacts produced by ReSTIR, with even 1 to 5 mutations providing noticeable improvements in image quality. We measure this improvement using the average radial covariance from every pixel. Now, though mutations help produce images with better visual fidelity, surprisingly, we observe that similar to blue noise sampling, they don't actually reduce mean squared error. We provide an analysis in the paper on why this is the case, but the gist is that we would need to mutate samples across pixels to reduce RMSE. Importantly, in scenes that do not contain any correlation artifacts, mutations never really make things any worse. Okay, so the key takeaway is that for problems with changing but correlated integrals, such as real-time rendering, it's often beneficial to apply resampling and mutations in conjunction to evolve sample populations. This is not a new idea. In the broader statistics and machine learning literature, a sequential Monte Carlo is a popular family of sampling techniques that combine resampling and mutations. Our work situates ReSTIR as a particular type of SMC algorithm applied to real-time rendering, and it opens the door to porting further improvements from statistics and machine learning. Finally, the recently published area ReSTIR paper further generalizes ReSTIR to solve the measurement equation, where, as with metropolis light transport, HI is a pixel filter. This generalization provides a nice framework for exploring how we can mutate samples across pixels, which should also help to not just reduce correlation artifacts, but also variance with MCMC mutations in ReSTIR. Thanks for listening.